It was a clear day over the Black Sea, just off the coast of Sinop. The sky was calm. The water below was flat and dark blue. High above it, 5 F-16 Fighting Falcon jets cut through the air in tight formation. Fast, controlled, familiar. But there was a sixth aircraft with them. It didn't have a canopy. It didn't have a pilot. No one sat inside it. It was flying on its own. Below them, a jet-powered target aircraft accelerated across the test range, fast enough to simulate a real enemy fighter. This wasn't a slow drone. This was a serious target. Inside the unmanned jet, the radar activated. Lock. The system calculated distance, speed, angle, closing rate, hundreds of variables in milliseconds. No human hand touched a stick. No pilot squeezed a trigger. A missile dropped from the wing. Ignition. The rocket motor flared bright. The missile accelerated past the speed of sound, racing toward a target dozens of miles away, far beyond what a human eye could see. Seconds later, impact. Direct hit. Clean. Precise. Controlled. And here's the part that stunned defense analysts around the world. Not the United States. Not China. Turkey. The aircraft was the Bayraktar Kızılelma, and it had just achieved what many believed was still years away. A verified beyond visual range air-to-air kill by an unmanned fighter. That's not a small milestone. That's a line in the sand. For decades, air combat dominance belonged to manned fighter jets flown by highly trained pilots making split-second decisions at 40,000 feet. Air superiority was a human skill. Now, for the first time, a machine proved it could detect, track, calculate, launch, guide, and destroy a fast-moving aerial target completely autonomously at long range. This wasn't a lab experiment. It wasn't a simulation. It was a live-fire interception. And if that doesn't sound dramatic yet, it should, because this moment may be remembered as the day air combat fundamentally changed. But before we go any further, there's an important question to answer. Haven't drones been firing missiles for years? When most people hear this story, their first reaction is simple. Drones already fire missiles. What's the big deal? It's a fair question. Yes, drones have launched weapons before. The MQ-9 Reaper has fired air-to-ground missiles for years. It has even tested short-range air-to-air shots. China has displayed missiles mounted on drones like the Winglong 3. The United States is developing advanced unmanned systems like the XQ-58 Valkyrie. So what makes this different? Distance, speed, and autonomy under real combat conditions. Think of it like this. Firing a short-range missile at a slow drone is like throwing a ball at someone standing 10 feet away. But hitting a fast-moving jet dozens of miles away, while both of you are flying at hundreds of miles per hour, is like hitting a bullseye from a football field away while both you and the target are sprinting. That's beyond visual range combat. BVR. In BVR engagements, the pilot often never even sees the enemy aircraft with their own eyes. Everything depends on radar, on data links, on complex calculations happening in fractions of a second. The missile doesn't just fire and forget immediately. It needs updates mid-flight. The launching aircraft must track the target continuously. If the radar loses lock or the data link drops, the missile can miss. This is fighter-level warfare. And here's the key difference. Most drones are too slow, too lightly powered, too sensor-limited. Traditional UAVs cruise at around 200 to 300 miles per hour. A modern fighter jet can exceed 1,200 miles per hour. That speed difference isn't cosmetic. It changes the physics of missile performance. Launching from higher speed and altitude gives a missile more energy, more range, and more lethality. Until now, unmanned systems simply weren't built for that environment. What happened off Sinop wasn't a drone swatting another drone. It was an unmanned fighter executing a genuine jet versus jet interception at extended range. That moves the conversation from interesting test to strategic shift. Because once a machine can fight in the same envelope as manned fighters, at speed, at altitude, at range, the rules start to change. So the next question becomes obvious. How did Turkey pull this off when much larger defense powers are still experimenting? This wasn't luck. It wasn't a one-off experiment. What happened over the Black Sea was the result of three major systems working together perfectly, like gears in a clock. If even one failed, the missile would have missed. Let's break down that chain. A. At the center of it all is the Bayraktar Kızılelma. This is not a slow propeller drone, it's jet-powered. It's designed for high altitude, and it's built to operate in the same performance space as traditional fighters. Why does that matter? Because missiles don't just rely on their own engines. They rely on the energy of the aircraft launching them. Imagine throwing a paper airplane while standing still. Now imagine throwing it while running downhill at full speed. It travels farther because it starts with more energy. The same principle applies here. Launching a beyond visual range missile from high altitude and high speed gives it longer range, better maneuvering ability, and a higher probability of kill. Most drones simply don't have that performance. Kızılelma does. And it was designed from the beginning with a loyal wingman role in mind, flying alongside manned fighters, extending their reach, and taking on higher risk positions. But speed alone isn't enough. You need eyes. The aircraft is equipped with the Murad ESA radar developed by Aselsan. ESA stands for Active Electronically Scanned Array. In simple terms, it's one of the most advanced radar types in the world. Instead of one big moving antenna, it uses hundreds or thousands of tiny transmitters. That allows it to track multiple targets at once, resist electronic jamming, update missile guidance in real time, and switch beams instantly. This is the same class of radar technology used on elite fighters like the F-35 Lightning II and the F-22 Raptor. That's a huge statement, because without a radar powerful enough to detect and track a fast-moving jet 30 to 50 miles away, none of this works. The radar doesn't just see the target, it predicts where it will be, and it keeps talking to the missile while it's in flight. But even that isn't enough. You still need the weapon. The missile used was the Doctrine, developed by TÜBİTAK Sage. This is Turkey's answer to the American AIM-120 AMRAAM, one of the most widely used beyond visual range missiles in the world. Doctrine uses active radar homing. That means the aircraft guides it mid-flight. In the final phase, the missile turns on its own radar and homes in independently. Fire, guide, confirm, impact. And here's the strategic detail that makes this even more important. The aircraft is Turkish. The radar is Turkish. The missile is Turkish. That means no foreign export restrictions, no supply chain vulnerabilities, no political limitations. It's a complete, self-contained combat ecosystem. Building one advanced component is difficult. Building three advanced systems that talk to each other seamlessly and proving they work in a live interception is something only a handful of nations can do, which raises a serious question. If this capability is so powerful, why hasn't anyone else demonstrated it publicly before? Because solving one piece of the puzzle is hard. Solving all of them at the same time? That's another level. From the outside, a missile launch looks simple. Radar lock, button press, boom. But behind that moment are four massive engineering problems, and solving just one of them can take years. Turkey didn't just solve one. They solved all four at the same time. Let's walk through them. Barrier 1, the speed and altitude problem. Most drones fly like small commuter planes. Steady, efficient, not very fast. That's fine for surveillance. It's fine for ground strikes. It's not fine for beyond visual range air combat. BVR missiles depend heavily on the energy they inherit at launch. If you launch from 40,000 feet at near supersonic speed, the missile starts its journey with massive kinetic advantage. It can fly farther, maneuver harder, and maintain speed longer. If you launch from 20,000 feet at 250 miles per hour, the missile burns fuel just trying to reach optimal speed, It's like starting a race halfway up a hill versus starting at the bottom. Traditional UAVs simply don't operate in the fighter envelope. The Bayraktar Kızılelma was built specifically to solve that. Jet propulsion, high-altitude performance, fighter-like launch conditions. Without that, the rest doesn't matter. Barrier 2. The radar power and cooling problem. Advanced AESA radars aren't lightweight gadgets. They require serious electrical power and generate significant heat. Fighter jets like the F-22 Raptor and F-35 Lightning II are designed around powerful engines and cooling systems that can support those radars. Most drones aren't. They were never designed to power high-end, multi-target tracking systems like the Murad AESA from Aselsan. Installing that level of radar into an unmanned platform means redesigning power generation, thermal management, and onboard processing. It's not plug-and-play, it's structural. Barrier 3, the secure data link problem. Here's something most people don't realize. When a BVR missile launches, it doesn't instantly go fully autonomous. For much of its flight, it relies on updates from the launching aircraft. Those updates correct for target maneuvers and refine intercept geometry. If that communication link is jammed, interrupted, or delayed, even for seconds, the missile can lose its edge. Now imagine maintaining that connection, at long range, at high speed, while maneuvering in an environment potentially filled with electronic warfare. That requires encrypted, jam-resistant, high-bandwidth data links. For a manned fighter, that's already hard. For an unmanned aircraft relying entirely on digital systems, it's even more critical. Break the link, you break the shot. Turkey demonstrated that the link held. Barrier 4, autonomous fire control software. This might be the hardest problem of all. In a traditional fighter, the pilot works alongside mission computers to decide when to fire, at what angle, within what no-escape zone, considering speed, distance, and target behavior. These are split-second tactical decisions. Now remove the human. The software must detect the threat, classify it, calculate intercept geometry, determine optimal launch timing, guide the missile, confirm impact, all in real time. That's not basic autopilot code. That's combat-level decision-making logic. And here's the important part. Solving one of these challenges is impressive. Solving two is rare. Solving all four, speed, radar power, data link integrity, and autonomous fire control, and proving them in a live engagement, that transforms this event from "we tested a missile" into an engineering breakthrough. Which brings us back to that formation over the Black Sea. 5 manned fighters, 1 unmanned. That image wasn't symbolic. It was a preview. Let's go back to that image in the sky. 5 F-16 fighting Falcon jets flying in formation, and beside them, 1 Bayraktar Kızılelma. That wasn't for show. That was doctrine. For decades, air combat has revolved around one principle: protect the pilot. Fighter pilots are some of the most expensive and highly trained assets in any military. It can take years and millions of dollars to train just one. Now imagine shifting the risk. Instead of sending a human pilot into the most dangerous airspace, the front line of enemy radar coverage and missile threats, you send the unmanned aircraft first. That's the loyal wingman concept. Here's how it works in simple terms. The manned fighter stays slightly behind, in a safer position. The unmanned jet pushes forward, it scouts, it detects threats, it even fires first. The human pilot becomes a mission commander rather than a trigger puller. It's similar to how modern generals don't fight on the front lines. They coordinate from a command center. The pilot's role evolves from direct combatant to battle manager. The United States has been working toward this idea for years through programs like Skyborg and the Collaborative Combat Aircraft Initiative. The goal is the same: autonomous jets that fly alongside manned fighters, extending sensor range and carrying extra weapons. But most of these systems are still in development or early testing phases. What happened off the coast of Sinop suggests something different: operational proof. An unmanned aircraft didn't just fly nearby. It didn't just simulate. It executed a real beyond visual range interception while integrated with manned fighters. That changes the conversation. Because once unmanned jets can perform real combat roles, detect, track, fire, and kill, they stop being experimental add-ons. They become force multipliers. And force multiplication is how military balance shifts. One pilot commanding 2 or 3 unmanned fighters suddenly has the combat reach of a small squadron. That's not just efficiency, that's transformation. Which leads to a bigger question. If unmanned fighters can extend reach, reduce risk, and potentially cost less than traditional stealth jets, what does this do to global air power? Air superiority is the foundation of modern military power. If you control the sky, you protect your ground forces, you secure your ships, you deny the enemy freedom of movement. Every major conflict in the last 50 years has proven one thing: the side that dominates the air usually dictates the outcome on the ground. For decades, that dominance has been incredibly expensive. Take the F-35 Lightning II. It's one of the most advanced fighters ever built. But it costs tens of millions of dollars per aircraft, plus enormous maintenance expenses. And not every country can buy it, either due to cost or political restrictions. Now imagine an unmanned fighter like the Bayraktar Kızılelma entering the export market. If it can fly at fighter speeds, carry advanced missiles, operate autonomously, integrate with manned aircraft, then it offers something powerful, high-end capability at potentially lower cost and lower political dependency. And here's where it gets strategic. The aircraft is Turkish. The radar is built by Aselsan. The missile comes from Tubatak Sage. That means Turkey controls the entire supply chain. No foreign veto power, no sudden export bans, no dependency on external software updates. In today's world, that kind of autonomy is rare. Many countries rely on multinational supply chains for critical defense components. If political tensions rise, those supply chains can become leverage points. Turkey has just demonstrated a fully indigenous air combat ecosystem: fighter platform, AESA radar, BVR missile, and autonomous integration. That puts it in a very small club. Only a handful of nations can design a high-performance fighter aircraft, an advanced AESA radar, a modern beyond visual range missile, and integrate them into an autonomous kill chain. Even fewer have publicly demonstrated all of it working together in a live interception. This shifts more than technology. It shifts perception. Defense planners in Europe, the Middle East, Asia, they're all watching. Because if unmanned fighters can deliver credible air superiority without the price tag or political strings of traditional systems, the global market changes. And when the market changes, alliances, procurement strategies, and military balances can shift with it. But this isn't just about hardware or exports. There's a deeper question forming underneath all of this. If machines can now fight at the highest level of air combat, what happens to the role of the human pilot? For over a century, air combat has been deeply human. From the dogfights of World War I to modern stealth operations, the fighter pilot has been the symbol of air power: skill, instinct, courage at 40,000 feet. Now we have to ask a difficult question. If an unmanned fighter like the Bayraktar Kızılelma can detect, decide, and destroy a target at beyond visual range, where does that leave the pilot? At first glance, it sounds like replacement, but it may actually be evolution. Think about how warfare changed with drones in ground combat. Soldiers weren't removed from the battlefield entirely. Instead, they gained new tools. Surveillance improved, precision increased, risk shifted. Air combat may follow the same path. Instead of being the one who flies into the most dangerous airspace, the pilot becomes the commander of a network. One human, multiple unmanned aircraft. The pilot's job shifts from physically maneuvering in a dogfight to managing sensors, approving engagements, and coordinating autonomous teammates. It's less about pulling G-forces, more about information dominance. But here's where it gets complicated. Autonomous systems operate at machine speed. In a high-speed BVR engagement, decisions happen in seconds. Radar locks, data updates, missile launches, impact. If AI handles targeting calculations and firing solutions faster than any human could react, how much authority should it have? Should a machine be allowed to fire without human confirmation? What happens in electronic warfare environments where communication with the human controller is delayed or jammed? These are not science fiction questions anymore. They are policy questions, legal questions, moral questions. We're not just replacing aircraft. We're redefining combat authority. Who makes the final decision to use lethal force, a person or an algorithm? And if nations begin trusting autonomous systems more and more, air combat may shift from pilot versus pilot to code versus code. That's a fundamental change in how wars are fought. Which brings us back to that moment over the Black Sea. Because whether you see it as progress, disruption, or something more complex, it may be remembered as the moment unmanned fighters stopped being experimental concepts and became operational reality. Let's return to that moment. Clear skies over the Black Sea, a missile streaking forward at supersonic speed, a target aircraft dozens of miles away. Impact. Off the coast of Sinop, something changed. The Bayraktar Kızılelma didn't just launch a missile, it crossed a threshold. For years, unmanned fighters were described as the future, promising, experimental, almost ready. But that day proved something different. The future isn't coming, it's here. This wasn't a publicity stunt, it wasn't a simulation, it wasn't a computer animation. It was a complete kill chain, radar detection, autonomous targeting, missile guidance, and confirmed destruction, executed without a pilot in the cockpit. That matters. Because throughout history, air power has defined military dominance. The introduction of radar changed warfare. Jet engines changed warfare. Stealth changed warfare. Autonomous air-to-air combat may be the next shift on that list. And shifts like this don't happen gradually. They happen in moments. Moments that, years later, analysts look back on and say, that's when it started. So here are the real questions. Does this change the balance of air power? Will air forces in 2040 look radically different from today? Will future fighter squadrons include more algorithms than aviators? Or will human pilots remain at the center, just commanding a new generation of intelligent machines? One thing is certain, the era of unmanned fighters is no longer theoretical. It arrived at Mach speed, and the rest of the world is now racing to catch up. What do you think? Are we witnessing the beginning of a new air power era, or just the first step in a much longer evolution? Let me know your thoughts.